all these parks are amazing features, and there's so many of them that this series will continue for a long, long time.
Yes.
But they always point us back to the flood, and it also points us back to the truth of the Bible. It also points us back to Jesus, who's the author of the Bible, the author of creation, the author of the judgment of the flood. But he's offered us salvation through his sacrifice, and by dying for us, took our place on the cross. He offers that salvation for all eternity for all of us.
Hello, everyone. Welcome to the Creation Podcast, the show where we discuss the science that confirms Scripture. I'm your host, Trey. America is home to many stunning forests, mountains, monuments, and other wondrous features. The unique beauty of many of these locations have prompted state and federal governments to designate them as state or national parks. Thousands upon thousands of travelers visit these locations each year to experience their awe-inspiring grandeur. But where did they come from? Many scientists claim that they formed slowly through uniformitarian processes. But is that true? Join us as we journey through the parks across America. In our first couple of episodes, we discussed America's oldest national park, Yellowstone, as well as some other prominent national features. Today, we're going to discuss two more national parks, both of which show evidence of catastrophic flooding. To discuss this with me today, I have ICR's resident geologist, Dr. Timothy Clary. Thanks for being here, Dr. Clary.
Oh, it's great to be here.
Awesome. We love talking about rocks.
Oh, you know it.
Yeah. Okay. So let's just jump right into it.
Okay.
We've got two national parks to cover today. If you haven't seen the first two episodes in this series, you should. But first, we're going to talk about Hot Springs National Park. So this is the second smallest national park, just under 9 square miles, so pretty tiny in Arkansas. It became federally protected in 1832, although it earned the title of national park in 1921. So, hot springs. What is a hot spring?
Well, a hot spring is anytime you have water, above normal temperatures. Groundwater normally will be the temperature of the average temperature of that area, whatever it is. So generally groundwater is cooler than surface waters. But then as you go deeper into the earth, the water gets hotter because the earth gets hotter as you go deeper. So what these are waters that are getting to the surface of the earth from maybe several thousand feet down, thousands of feet down, that come up along a fault or a fracture system, and so they're able to kind of follow a pipeline and rapidly get to the surface. And they generally contain a lot of minerals, because the hotter the water, the more it can dissolve solids. And as those come up to the surface and they cool, of course, they precipitate. Many of the hot springs give you the rotten egg smell, which is really very, very small amounts of hydrogen sulfide, which is a deadly gas. But if you can smell it, it's not high enough to cause any damage.
Right.
If it's really strong, and people die from this in the oil and gas business, sometimes they'll drill into some of these gases and they get released. You really can't smell it. It's just too strong, and all of a sudden you're dead. you can die very quick.
Okay. All right. So when this park was originally surveyed, they counted 70 springs. Today, 47 of them are still going, I guess we could say. They produce 750 to 950,000 gallons of water. And water temperatures range from 95 to 147 degrees. Some of that seems actually pretty pleasant. Mm-hmm. Not as forbidden as some of the hot pools at Yellowstone.
Mm-hmm. Right. Those are deadly. Some of those are deadly if you fell into those. But this is typical of hot springs that aren't caused by magma. And so this is, again, just coming from water deep in the earth that's been heated really by the Earth's internal heat, probably several thousand feet down, that gets to the surface pretty quickly.
Okay, so we have hot water. We have 47 out of 70 original springs. We know what a hot spring is. How do conventional scientists claim that this all came about?
Well, they think, of course, over millions and millions of years. They're always throwing those millions of years in there. And the rocks there are thought to be, several 100 million years old, if I recall correctly. So they think these are deposited slowly in oceans, and as the oceans advanced across the continents, and then deposited these rather unusual rocks we'll be talking about here in a minute. But the rocks themselves, and then of course later they were folded up and faulted, and different things happened as the continents collided. But all this took place over millions and millions of years. That's the conventional story. Our story as creationists is a little different. Of course, we don't believe in the millions of years, but we also have better explanations, I think, for some of the features we see there as well.
Right. And so we have just 3 observations that kind of demonstrate how Hot Springs National Park is better explained by a recent global flood. And so we'll start off with flood rocks at the hot springs. So chert, which that's a rock. That's a weird name.
Yeah, well, it is. Sometimes it's called flint. Other people call it different things. I think there it's called novaculite, which is similar to chert, but not quite the same. But chert is what a lot of arrowheads are made out of. Stone tools are made out of chert. People, they dispersed from the Tower of Babel. They didn't have the metals. They didn't know where the metals were yet to make, bronze and things like that. So they used stone tools. And many cultures continue to use those even up through today. But the chert is often the number one tool to make these arrowheads or spear points or even knives. It's a quartz rock. It's a microcrystalline quartz, very, very small crystalline quartz. And you can make very sharp edges if you chip it just right. And so you can get these kind of almost like a serrated edge to some of these. And it's really durable. Quartz is one of the more durable minerals. It's actually most common hard mineral out there on the earth. That's why beaches are made out of quartz sand, because it's very resistant to erosion. It's on the hardness scale, it's a 7 out of 10, diamond being a 10. And so, but it's very, very common. It's found throughout the Earth's crust, and therefore it's found in many of the sediments that were formed during the flood year. And some of this unusually forms this strange microcrystalline version of quartz called chert. And that chert is a mystery even to the conventional geologists, really how you get layers of chert forming. Most people think it might be in the deep ocean, but nobody really sees today chert layers being deposited, other than maybe some of these single-celled organisms that are made out of quartz shells sinking to the bottom of the ocean and maybe making like a quartz ooze at the bottom of the ocean, and then somehow that becomes chert. But chert has been a mystery since I was in school. It's been a long time. I don't think they've really solved the chert issue. Where does chert come from? Other than people pretty much assume it's formed in the oceans, or a marine rock, as we call it.
Okay, so chert being at the hot springs, how is that indicative of a global flood?
Well, the chert we see there was deposited in some of the early layers of the flood. And so there's this massive chert deposit that covers a large area of the southeastern United States. And to get that scale of chert, again, chert itself is a mystery, but to get that scale of chert is even a bigger mystery. And I think the flood might have had some sort of different temperatures to the water, obviously. When the fountains of the Great Deep burst open, we have all these mineral-rich waters coming out. Some of this might have contained the quartz that we need to make chert. And so I think the flood offers, maybe we don't have maybe all resolved, but it offers a better explanation for the extent, again, of this chert layer. It's a very massive, massive layer. And I mapped it out in some of my research. As I was going through the columns across North America, you can see there's a couple of times in the history of the United States and the history of North America where you see a massive chert layer, and this is one of them. And again, it's exactly why you get the extent of this chert is kind of a mystery to the conventional scientists. But I think the flood offers us a better explanation for the massive extent of it. Right. It had to be some unique chemistry of the water, no doubt, but to get the extent of this, again, it's like another thin layer. I mean, it's not that thin, but it's compared to the size that it covers. Just like these blanket sands we've talked about in previous episodes, blanket deposits. It's another fairly extensive layer that happens to be right there at Hot Springs National Park. Very small park, because so much has been developed around it. And fortunately, the government has been kind of preserving this since the 19th century, or we wouldn't have anything there at all. So,
yeah, absolutely. there's also another feature that just kind of, and we talked about it a little bit in other podcasts, but we're going to talk about it again a little bit. So folding of sediments, because rocks don't fold, right? So what kind of folding and faulting do we see at Hot Springs National Park, and how is that indicative of a global flood?
Well, again, we see intense folding. We see rocks that are, tilted, folded in very, very tight folds. And you can see these as you drive around the park. In the eastern U.S., there's more vegetation, but there's still a lot of places where rivers cut through, where road cuts go through, and you can see these intensely folded rocks. And even folding the chert is difficult to do. So these layers, again, chert's very brittle. All rocks, in fact, are very brittle when you try to fold them and break them. Imagine trying to, fold a spear point. It's just going to break. It just snaps in half. And so even though it's a tough rock, when you try to fold it, it's going to break. And so we see the sediments in Hot Springs, many examples of the folds, intensely folded terrain. What we think was happening was there was some sort of continental movement going on. You had some sort of collision. And so you folded up these early deposited flood rocks into these kind of intense folds. And we see that exposed right where you go through Hot Springs.
Right, because rocks today don't fold, they shatter.
Right, rocks today, you try to fold them. Again, I encourage people to try this at home. Try to fold rocks. Try to get a layer of rock and then just try to get a piece of sandstone or a piece of limestone and try to fold it. It's just going to break. And that's exactly what, when you try to push rocks or fold them or squeeze them like that, they generally just shatter. They're very brittle at the surface. You have to be down really deep in the earth, miles and miles and miles down to get rocks to fold. And I don't think even the conventional geologists suggest that. Many of these are involved in thin skin thrusts, which is another term that may baffle the listeners. But those are just where you have rocks that have actually moved somewhat horizontally, massive sheets of rock, just sediments. So they're called thin skin because they don't involve the crystalline basement rocks, as we call it. And so you have these massive movements of these sediments that actually cause intense folding at the front ends, almost like a landslide. And so we think these things kind of slid down. Conventional story is they were pushed, but again, you can't push rock, nor can you fold rock if it's really rock. So these had to be kind of slides from this collision going on. You had things that can slide on water pressure. Just like water between two plexiglass sheets, you can get things to move really easy. Or if sometimes you put your soda can on the table and it'll start to slide a little bit, you notice, because the water gets trapped underneath there and starts to move, even on a very, very flat angle, almost 1 or 2 degrees. And so some of these features we think are better explained by the flood, including the thin skin thrusts, to preserve the water pressure you need to make those. They can't have moved slowly over millions of years. And so you've got to move these things quickly. And to get the folds we see, they had to be near the surface. They weren't deep. And if you're moving things quickly, you're folding things quickly, the only way to do that is if the sediments were still unlithified or uncemented, still packed down from the flood, but still soft.
Gotcha. That makes a lot of sense. And if the flood was occurring, then we would also expect to see erosion as well, right? Flood erosion. Do we see that?
As the water receded, right? The water did recede off the continents. The Bible talks about that in Genesis 8. There was a receding phase of the flood. And to get those kind of rocks like that, and some of these are making linear ridges. Like there's one right through the middle of Hot Springs. There's a river that cuts through this uplift. So these rocks were uplifted, and as the water receded, it left behind these remnants of these nearly vertical folded rocks. But there's one spot where a river cuts right through this. Why would the river cut through a big, massive uplift? It should have gone around it. And the reason it went through it is because I think the water was above it at one point, and these mountains and rocks were being folded while they were still soft. And water was receding off the continents, leaving these little remnants sticking up. And some of these rocks cracked. In addition to folding, sometimes there are often a lot of fractures and cracks along with them. And water just followed that crack and cut right through it. So today we see this little bitty stream going right through this big uplift that runs right through the Hot Springs National Park. And people don't often question that. Why does the river cut through it? This little tiny stream today. Why wouldn't the stream go around? We see this all over the American West. You can go into Yellowstone National Park. You can see Rattlesnake Mountain. There's this big, massive uplift, and the river cuts right through it. Why does it cut through these things?
Because water's going to take the path of least resistance.
And it should go around these features. My dissertation area down in Royal Gorge, Colorado, big uplift comes up and the river cuts right diagonally right across it. Why did it cut across it? Why didn't it go around it? And it's because the water at one point was above these features, and these rocks were being folded and cracked, and the water, as it's coming down, found those cracks and just zipped right through it.
As opposed to the conventional idea that the water eroded that channel over.
Right. Or they'll say you had to have two streams on each side of the little uplift, the little hill that runs through, and they have to have streams that just happen to coincide with each other, and finally one takes over the other. They call stream piracy or something like that. But they're calling out a lot of coincidences because we see this all over the American West, all over the world. We even see it at Grand Canyon National Park. There's the Kaibab uplift at the beginning. The eastern side of Grand Canyon, there's a big uplift that went up a couple thousand feet, and the water cuts right through it. Why would it go right through that and not go around? But if there's fractures there, the water can follow those fractures. So we see that over and over and over again across the American West, and we see it at hot springs. There's rivers cutting right through uplifts, a linear ridge sticking up, and the water cuts right through it. Why does that happen? And the conventional stories that they give at the parks never explain that.
Right.
Or else they'll try to say, over millions of years, this little bitty stream, Kenny wrote all that, just like we talked about at Devil's Tower. This little bitty stream is supposed to erode away, miles and miles and miles of material and transport it so far away you can't even see it. And the same thing is true here. Why would streams cut through these uplifts and not go around them? Yeah. Other than the water had to be above them at one point, and it came down, found a fracture. As the water lowered its level, it kind of channelized through it and just stripped that, kind of cut the fracture bigger and bigger. So today we see rivers cutting through uplifts, but that shouldn't happen if it wasn't for the flood.
Okay, so we've discussed kind of how this is evidence of a global flood. Let's talk about the geothermal system that kind of powers hot springs. I think that's an incredibly intriguing part of the whole system. How does it work? How does hot water continue to pour through here, gallons upon gallons upon gallons, without falling apart? I mean, some of them clearly do, because again, 70 hot springs originally surveyed. There's fewer now. So how does this work? What is the mechanism that keeps this going?
The mechanism is really the hydrologic cycle that God set up in the post-flood world, and there was some sort of similar hydrologic cycle in the pre-flood world. He talks about how mist came up and water came up to water the plants. But in this case, we can study the post-flood world because we're in it. And so we can actually see that as rainfall comes down and snow comes down in some of the mountainous areas, particularly in the south, it's more rain. You see you're kind of recharging is the right word, the recharge of your groundwater. And so water's percolating down, water's following fractures down. As it comes back up, of course, it has to displace some of that water. And some of that water is then, because of these mountains that were forming during the flood, these fractures that formed during the flood, water is able to follow those fractures almost like following plumbing, and comes up to the surface, bringing these really hot waters that form originally from surface water coming down as rain, recharging groundwater, the water table, and that water slowly sinks down, moves and transports. Groundwater is always moving. It's always, it's being, depends how much water you add. Sometimes it's moving faster than others, but it's always flowing. And so groundwater is always percolating through the rocks. And if it follows fractures, it's going to go even faster. And so as it percolates down slowly, the water gets heated from the Earth's internal heat, and then it's able to follow those fractures up very quickly to the surface. So you kind of have a continuous cycle of water coming in, water going out. But it's all driven by rainfall and precipitation. If you stop the rain, your groundwater table starts to drop and drop and drop. But because we get sufficient rain in the southeast of the United States, we get a lot of recharge of these hydrologic systems. Some of those exposures, I think, were also modified by human activity. They've kind of destroyed some of the springs, and so that's part of the reason why. But there are springs that stop. There's springs that the water will change direction, or changes groundwater flow direction for whatever reason, and some of that's due to long-term changes in precipitation over maybe many decades, and you just get some shifts along certain fractures may precipitate out minerals and kind of seal them off, and so water has to find a different path. And so there is some dynamic nature to some of these springs. But it's amazing how consistent they are. And that's driven by the hydrologic cycle that our Lord put into place to supply our needs. We get half of the world drinks groundwater. The rest of us drink surface water if you're not. But surface waters, many of those are also supplied by groundwater. Mm-hmm. Most rivers are supplied by flow from groundwater, lakes that aren't dammed up, where you're artificially, stopping the water flow. If it's a natural lake, it's fed by groundwater. And so groundwater really is very, very important. We just don't think about it much.
Right.
But
because it's underground.
It's underground. And the deeper you go, the more minerals that water picks up. So when we drink groundwater, we drink the surface, the first layer at the surface, because it's the freshest, because it comes from the rain. But as it goes deeper and percolates down, it starts to dissolve more minerals. And so water produced, say, with oil wells, they're thousands of feet down. They're very brine-rich, they call it, even more salty than the oceans.
Oh, wow.
So that's why many of these minerals that come back up now, the water's hot, but they contain a lot of minerals.
Well, thanks for talking me through that. It is really a beautiful place. I've been there. It's fun to see. It's almost like, I don't know, hot tubs are a thing, right? Mm-hmm. Humans have kind of like made our own version of this where it's like, hey, this is just really cool. Like hot water is cool as long as it's not too hot, right? And it's there, it's beautiful, and it's evidence of the flood.
Well, it's evidence of the flood, but it's also evidence of the hydrologic cycle, which was our Lord put into place. At least we understand how the one works now. In the pre-flood world, we're not so sure, but it's an amazing combination of things: of flood rocks, rocks that were folded in the flood, the fractures that formed in some of those to allow water to kind of cut through as the receding phase was progressing along, and leaving the remnants that we have today. Yeah. But again, there's many reminders of the flood, even at hot springs. Just like almost all these national parks and monuments, most of them were either formed or carved by the floodwaters.
Yeah, absolutely. Well, do you have any final thoughts on hot springs?
Well, Hot Springs is an amazing little park. It's pretty popular because it's in such a populated area of the country. So it's there's a lot of make reservations if you're going ahead of time. But there's again, when you read the signage at the park, don't believe everything they say. They're giving you the conventional evolutionary story. It's best if you had either ICR's article or watch this broadcast, so you have some idea what you're going to see. And so you can look for these features yourself. You can look for the gap in the hill, and you can see where the water today cuts through this tiny little gap in this big, almost like a mountain that stands up there. And you can see the evidence of the folded rocks as you drive around, evidence that these were folded while they were still soft and not that long ago. And even the hydrologic cycle, it's still in operation. As groundwater tables change and fluctuate, of course, this whole system may shut down.
Right.
And how long it's going to last, nobody knows, but it's been going on for hundreds of years. Yeah. And it probably will continue for hundreds of years more as long as we get sufficient rainfall in the area, which seems to be not changing too much. Yeah. So I think it'll be good. So again, this is like all the parks. There's always an alternative story they're not telling you when you go to the national parks. The national parks will just tell you the conventional evolutionary story, but there's always another side to that they're not telling you. But if you look for these features, as you go around the country to visit the national parks and monuments, there's all these features that we pointed out, plus others. That'll help you realize that these are a product of the flood. And only the flood can do these types of things and create these types of folds, these types of gaps in the mountains. People call them water gaps, but these are features that only the receding phase could make. And
they could also just rent you out for the day, be like, hey, Dr. Clary, come with me and explain all these things.
Well, yeah, I can do that.
You could do that? Okay.
No, I actually have to get a lot done, so I can't be dragged out of the office as much as I'd like to go. I'd like to go out and see more parks. I've been to Hot Springs, I think twice. Now I'm going to hope to go again soon. But it's all these parks are amazing features, and just there's so many of them. that this series will continue for a long, long time.
Yes.
But they always point us back to the flood, and it also points us back to the truth of the Bible. It also points us back to Jesus, who's the author of the Bible, the author of creation, the author of the judgment of the flood. Yeah. But he's offered us salvation through his sacrifice by dying for us, took our place on the cross. He offers that salvation for all eternity for all of us.
Absolutely. And we encourage anyone to, if you have any questions about that, about the faith, please email us, contact@icr.org. We'd be glad to talk to you. Let's move on to Badlands National Park.
Okay.
That's our next big park that will cover the second half of this. So this became a national monument in 1939 and then a national park in 1978, which you had mentioned in the previous episode, the difference between a national monument. The president can just say, hey, it's a monument. We're a national park, act of Congress.
I believe that's how it works.
Okay, so that makes sense. Badlands National Park hosts over 1 million visitors each year. It's named Badlands because the Native American Lakota people called it that in their native language, and the French fur trappers called it Badlands to travel through. So it doesn't sound super fun, super inviting. Mm-hmm. Although early people groups might have had little use for this very rugged terrain, it does contain spectacular features that exhibit flood depositional processes. So let's talk about that. First off, let's talk about clay. What's exciting about clay?
Well, clay is the most common sediment. Many of our rocks erode away. Many of the crust of the earth erodes away into clay minerals. So there's a lot of clay minerals. A lot of erosion results in clays. And sometimes you get sands in there and other things, but clay is the most common one. And it's sticky. And some clays, actually, from volcanic deposits, like we see at Badlands, they actually will swell when they get what the mineral's called bentonite. And those minerals, when you get wet, they actually swell, and then when they dry, they contract again. And that's causes a lot of foundation problems here in Texas, all the way up through the Rockies.
Right. Which is why we can't have basements here in Texas. Right.
Ironically, you have tornadoes and no basements.
Right.
So I'm used to basements growing up in the Midwest, where everybody has a basement. We don't have as many tornadoes. But.
Yeah. I always thought watching shows where people had basements, I was always like, when I was a kid, I'd be like, oh, it'd be so cool to have a basement. Nope. Never had one.
Yeah.
Yeah. Okay. So clay, very common. Uniformitarian scientists say that they were deposited over long periods of time out of stagnant water, right? So water that's just sitting there. It does settle out of stagnant water today at times, but what's different about the clay that we see forming now and what you would expect to see from a global flood?
Right. Like you said, it is settling into lakes and things today that are pretty stagnant. You do see slow deposition of clays. You shake up a tube of water, has clay in it, you'll see it gets all muddy, and then you come back the next day, you see a little layer of clay at the bottom that settled out, and the water looks clean again. But that's not what happened to make the rocks that we see. And so we look at the rocks, we see these thin little layers of clay called laminations, really thin layers. They're just like 1/8 of an inch or 1/16 of an inch, sometimes a little bit more or less, but nonetheless, really thin layers. To get thin layered clay like that, flume experiments done in the last 20 years by conventional scientists have shown that you got to have moving water. So oddly enough, the clays that we see all around the world in Badlands had to be moving water, had to be deposited by not really super fast water, but water moving maybe a foot or so per second, which is fast enough. That's this far every second zipping by. So not as fast as maybe sands, which maybe require a little bit higher speed, but definitely you can build up a lot of clay very quickly. And they found out in the studies that clay will actually flocculate or collect together when the water's moving like that, and forms almost like little sand-sized material. So the clays will kind of stick to each other and settle out, and they're almost like little miniature sand grains, but they're clay minerals. And so when they get compressed, they show these layers. And to get those layers, you got to have moving water.
Right.
So that's not what made the rocks full of clay at Badlands or most places in the world. That's what's happening maybe in lakes today, but that's not the same process. So the idea that all these layers took, millions and millions of years to form a few hundred feet of clay or shale, as it turns into as the rock is compressed, it becomes shale rock and cements together a little bit. Those don't take millions of years.
Right. In fact, they can't happen over millions.
Right. You've got to deposit these quickly and by moving water. And there's other evidence of quick deposition in Badlands as well.
Yeah, for sure. Okay, so speaking of quick deposition, there's a unique feature called a clastic dike, which I feel like you may have explained this to me before.
Maybe.
It's carved in stone. It's in that DVD.
Yep.
Hold it up.
Yeah, it's in here. We go to Badlands in this DVD. We talk about it there.
Yeah.
And so if you didn't get enough on this episode,
There you
want
go.
to pick this up, and we're actually out there in the field looking at this. I've been to Badlands National Park at least 10 or 12 times.
Wow.
And every time I go, it's very scenic, very beautiful, but it also shows these features we're talking about
Yeah.
that you can see all over.
Yeah, so what is a clastic dike?
Well, clastic dike is a material in geology. We talk about clasts. Clasts are anything that's not dissolved. So clay minerals are clasts, sand grains are clasts, silt, which is in between the two. Anything that's cobbles and things like that, those would be clasts.
Okay.
And so these are dikes, and dikes are a feature that cuts across layers.
Okay.
And so oftentimes they're vertical or near vertical, just like magma intrusions come in almost vertical or near vertical. Sometimes they call those dikes. These are clastic dikes because they're made out of sedimentary material, made out of sands, clays, and sometimes even small stones. And how they occur is you've got to de-water something very quickly, bury material so fast, deposit things so fast that you've got all this trapped water. And after a while, as you bury things deeper and deeper, the water compresses and it actually will fracture the rock, fracture the sediment, and squirt up along these little intrusive dikes, as they call them. And so some of that sediment actually goes up along with it. So when you see these dikes, they're full of clastic material that was down below that kind of squirted up along with the water coming up, high amount of water, but also carried a lot of these sands and clay minerals as well. So the rocks look a little different. You can see often maybe a little difference in color between the clastic dikes and the normal flat-lying sediments. And at Badlands, you can go around on some of the hikes and trails, and you see these are everywhere. There's a network of fractures. They're all filled with sedimentary material. And geologists would call them all clastic dikes, and they're all evidence that you had deposition so fast that the water got trapped and was able to shoot up along these fractures. It's really a network of these things all over. To me, it screams rapid deposition.
Right, because you have to have water coming in so quickly. And if this took place over millions of years, that would never occur.
And clay minerals, generally, when they're deposited, there's a lot of water in them. And so as they compress by more sediments, there's a lot of trapped water in there. So it's very common to see clastic dikes when you have a lot of clay-rich sediments. And that's exactly what we see at Badlands. That isn't pointed out normally by the evolutionary signage, because to explain them, they may say there's clastic dikes, but they don't explain how the clastic dikes form and why they form. They form because you have rapid deposition and rapid dewatering. The water is trying to escape to the surface, and it drags along sediment along with it, filling these fractures with sediments or clasts as they go. And to us, that is evidence of rapid deposition that happened during the flood year.
Yeah, absolutely. So we have clastic dikes, and next so there's a pretty unique feature in the Badlands that's kind of large, 60 miles long, actually, which is huge, comparatively speaking, and known as the Wall. Can you explain the Wall to me?
The Wall. Yeah, the Wall. There's actually a city called Wall, actually, on the east side. Badlands, by the way, is about 90 miles east of the Black Hills. And so if you go to the Black Hills, it's worth the drive out to the Badlands to see them, to drive through them. But the Wall is actually where the Badlands stop. And so the erosion that was taking place, we believe, during the receding phase of the flood kind of was eroding back to the west. And as it eroded, that's where it stopped. That's where most of the water finally was gone. So today there's this Badland topography, which are these small little hills, very rugged terrain. And Badlands are common in many places, but this one's pretty spectacular because it just stops at this wall. Mm-hmm. And so the wall is where you've had sediments that were deposited, these Badlands rocks themselves, which are pretty extensive. We talk about, again, extensive layers being evidence of the flood. Well, these Badlands rocks, they go not only in South Dakota, but they go down to Nebraska, and you can see same rocks at Scotts Bluff National Monument, at Chimney Rock. All these are the same rocks, and they go across into Wyoming as well. So there's the same rock unit that was deposited for a large area that's being eroded now. And as the erosion occurred, it went back to what's called the wall. So it's almost like you eroded away. Gullies are cutting back, and then all of a sudden the water's gone, so it doesn't cut back anymore.
Gotcha.
And so today it is slowly eroding, but not like it did as the water receded.
Okay. How do conventional scientists try to explain this?
Well, they try to, of course, explain the rocks being deposited slowly over millions of years and millions of years ago. And they also think the erosion is taking place over millions of years. But if that's the case, where did all the sediments go? You have these topography, this rugged gully type topography, little small hills, and then it just kind of ends. But if you go out east, there's nothing. It's just totally gone. And so for them to explain where did all that go, there's just not that many miles of Badlands that's up to the wall. But east of there, they're gone. You look out, you're at the park and you look out to the east, it's just flat. And all these rocks that you were standing on that makes the Badlands are gone. So it is just a very small area, even though it runs 60 miles north to south, so to speak. It's not that wide. And they're just gone. So to explain that, of course, they have to say there were rivers out there over millions of years. You wrote everything down to this perfectly flat plain again. And you see that over and over and over at many of the parks. They try to use these little rivers that are today to explain massive amounts of erosion. Mm-hmm. But they hide it behind this shroud of deep time. They say, well, let's get up here over millions of years. Well, rivers today don't do that. Rivers don't erode away massive parts of the landscape and leave little remnants behind. They would, cut away a gully or maybe they move around a little bit because rivers are dynamic, but they're not going to erode away an entire landscape.
Right.
And you need a lot more water, almost a sheet wash to erode that away.
Yeah.
And what we see at Badlands is really the ends of that, where the erosion occurred, and you have this little remnant just before the wall, and then the wall is a higher elevation where the Badlands rocks are buried underneath there. They're still there.
Yeah.
They're just not exposed by the erosion. But that's where the erosion from the flood came to a screeching halt. When the water was gone, of course, it stopped eroding. It's just eroding very, very slowly today. It is actually pretty quick. Dr. Gluz and I were out driving around the Badlands. We saw a benchmark sticking up from the 1940s. It's sticking up this high above the rocks. And so there is rapid erosion taking place. That eroded away in, 80 years, that much material. And so there is rapid erosion, even of the Badlands, taking place. But it's not nearly what they need to erode away all that landscape to the east of the Badlands, where it's just planed right off, right down to nothing. The rocks are totally gone.
To me, it seems like a lot of what we see in a lot of these national parks is just massive amounts of water moving massive amounts of sediment.
Yeah, the receding phase, but also even the deposition of these. Mm-hmm. To deposit these early in the receding phase, to deposit these sediments, and many of these contain a lot of fossils of mammals and things that I think were probably living at the highest hills. Yeah. Similar to what we saw in the Green River Formation, but more land animals in this case. But you've got these deposits that are very extensive, again. How do you explain these extensive multi-state deposits without a massive flood event? To explain them by rivers, of course, rivers don't just deposit pure sand across that, or in this case, clays that are so consistent, and sediments that are so consistent across that great distance. And we see the evidence of the classic dikes, that these are deposited quickly. And even to bury the fossils that are found in there, you got to bury things fast and deep. So all this tells us that these rocks are deposited quickly. The extent tells us they're deposited by some mechanism like a major flood. And then the erosion of these, the rapid erosion, removing all these rocks to the east of Badlands National Park. The entire landscape is just devoid of any of these. To me, all that is best explained by the flood, the year of the flood, the Now, the eroding, the receding phase of the flood really is responsible for what we see at Badlands National Park. The deposition of those rocks during the receding phase, earlier part of the receding phase, and the erosion of those rocks as the water continued to drop and cut more and more into these channels, back into the hills, creating the wall, but also removing everything east of the park.
So you had mentioned fossil mammals, and there are a lot of different kinds of mammals. And so, when I think of fossils, I think of, we have marine fossils, which make up most of the fossils, and then there's dinosaur bones, et cetera, et cetera. But there's a lot of different types of animals here. A lot of them are mammals, not all of them. And that makes them kind of unique, this collection kind of unique. We've got lizards, alligators, turtles, eagles, owls, gulls, pelicans, horses, camels, rhinos, tapirs, pigs, squirrels, beavers, rabbits, sheep, cats, and dogs. So we have this very varied, for lack of a better word, this varied assemblage of fossils. So what is it that makes this kind of unique?
Well, most of these animals you don't see mixed in with dinosaurs. There's a few mammals with dinosaurs. You see squirrel-like animals and beaver-like animals that lived in wetlands and lowland areas. And it kind of goes back to my flood interpretation based on my column research across the continents, that there's shallow seas in the pre-flood world, there's lowland areas where the dinosaurs were living, and then there's these upland areas. And I think most of these animals that we're looking at here at Badlands are from the uplands area, just like most of the animals in the grandeur formation, I think, were uplands animals mixed in with a lot of marine animals or ocean animals as well. But in this case, we have less of the ocean animals. We have more of just the animals that were stripped off the highest hills and transported down from what might have been originally Canada, might have been the highest hills. And those animals were washed down and deposited quickly with these clay-rich sediments of the Badlands National Park. So you're looking at a unique ecological zone that's above the dinosaurs because they were buried after the dinosaurs as the floodwaters went higher and higher. And so it all kind of fits the flood model that we don't find dinosaurs at Badlands because their ecologic zone was already completely inundated all over the world at the same time. And then you went to the next levels and you started washing out these animals from higher hills and washing them down on top of the dinosaurs and spraying them all over. So we see, lemurs up in Greenland, on the northern edge of Greenland, in those areas, and you see lemurs in Wyoming. These, because they were spread in all directions away from what's now Canada.
Right.
And so these are animals, I believe, are best interpreted as animals from the highest hills. That's why you don't see dinosaurs.
Yeah, that does make a lot of sense. And I think that it is interesting just in this location that there are no dinosaurs, because I know that when we think of fossils, we're like, dinosaur fossils. But then here they are, mammals and other things. So that's incredibly unique. And thank you for the explanation. As we draw this podcast to a close, do you have any other final thoughts on Badlands or just the national parks as a whole?
Well, again, the national parks are spectacular to go visit if you get the chance to go. Sometimes they get busy in the summers. Others are not so busy, like Fossil Butte. And the Fossil Butte area it's a very pretty area, but it also showcases the flood. So most of these places, again, when you read the signs when you go to national parks, be very wary because they're just feeding you the evolutionary story, the millions and billions of years story. But there's another side to this that they're not telling you. And so if they really look into what's there, the extent of these deposits, the evidence of rapid deposition, evidence of folding of the rocks, all these indicate this stuff happened at a very short time frame and not that long ago. And even the receding phase is showcased as you strip away the landscape east of the Badlands particularly. It's just gone. It's just everything's washed away, and it's washed away. Many of those sediments might have ended up even in the ocean, in the Gulf of Mexico.
It's too clean to have taken so long. Yeah.
And rivers can't do that. Rivers today can't clean a landscape up. They'll cut a valley, but they don't clean a landscape up that extensive.
Awesome. Well, thank you so much. We do have a couple of resources that we're going to mention. We mentioned them before, so we won't spend too long on them. But if you want to learn more about parks, we do have the Parks Across America book. It discusses many of the places that we're talking about now and more, right?
Well, we'll probably have a follow-up on this in another
A volume
shortly.
2.
There'll probably be a volume 2 and probably a volume 3 and a volume 4
Yeah.
in the years to come as we continue to write these articles. What's nice about the book is it gives you more pictures and more maps and things than what we put out on our Acts and Facts articles. And so it's a really nice collection. Like you say, it makes a nice coffee table book.
Yeah.
Something to get a conversation started.
Yeah.
When people start flipping through and they realize, wait a minute, you mean the flood can explain all this? The flood can explain it better? And then maybe they'll start thinking, maybe there is some truth to God's word. Maybe there really was a global flood. And that's exactly what we want to show, is that all of these parks show the global evidence of the global flood in one way or another.
Absolutely. And we also have a couple of resources featuring you.
Yes, I have this pondering look on the back.
Yeah.
But this is called Carved in Stone. It's a DVD that's about 70 minutes. I think it's 5 episodes, about 13 and 15 minutes each. And it goes across the national park. Actually, one of them is included, one of the episodes includes Badlands National Park, where we look at these classic dikes. We look at some of these features, and you can see the topography we're talking about in our podcast here. It also goes through Yellowstone and Devil's Tower and some of these other parks we've talked about as well. And if you want to know a lot more, I have this book that I wrote a few years ago called Carved in Stone, which includes 3 continents worth of data, North America, South America, and Africa. And this particular book really does show the evidence of the flood is global. It talks about the great unconformity. It talks about these different features in here. And it shows it step by step by studying the mega sequences across the continents and where the sediments are deposited from continent to continent. As you go through, you see lots and lots of evidence that there was a progressive flood. And the flood progressed up from the lowest areas to the highest areas. And that's why we see this ecological zonation. We talked about in this broadcast, why you see just mostly mammals in the uppermost flood layers, because that's what was being buried at that time. You already had buried and inundated all the shallow marine areas. Then you inundated the dinosaurs and the swampier areas of the world, the lowland areas, and then you went to the uplands. And that's what we see at Badlands National Park. So it really does fit when you think about it in terms of a flood. There's a progressive flood that took 150 days to get to the peak. My wife always wants to remind people the flood wasn't just 40 days, because we seem to get that idea by going to Bible school over years, singing songs. The flood was only 40 days, but that's not the case at all. It was 150 days of rising, according to the Bible, and then you had another over 150 days of receding. And so the animals and Noah and his family was on the ark over a year before they were able to get off. The water took at least maybe 313 days before it was drained off. And then they had to wait a little longer for vegetation to grow before they were allowed off the ark, because all the food would have been still in the ark until vegetation grew enough the animals could go out there and graze. And so God had a plan to restore the earth as well. And it's an amazing part.
Yeah. It's kind of crazy to think about living on the ark for a year. Wow. I also want to plug the Creation on Location series that we have here on YouTube. It does feature some of our scientists going to on location. Going on location and speaking about different features that we see. Some of these that we've mentioned here, but it's different when you see it in video format there with the scientists right there. So
we'll have one on Hot Springs, I think, shortly.
Yeah, okay.
And we've done some on the Green River Formation. We've done Badlands. We've been to, like I said, not only in the DVD, but I think we have some creation and location of some of these as well.
All right. So there's a lot to see, a lot to do. So thank you so much for being here, Dr. Clary.
Oh, you're more than welcome.
Awesome.
It's always a great pleasure to do these.
Yeah, absolutely. And we love having you on. So. And thank you to all of our listeners and viewers for tuning in for this episode of the Creation Podcast. If you found this encouraging or interesting in any way, please make sure to like, subscribe, share. If you want to get the Creation Podcast a week early, or our other podcast, Creation.live, 2 weeks early, you can become a member here on YouTube or on Patreon. There's other little perks that you can get depending on which tier you join from. And so we encourage you to do that if you want to just learn more and access more. So we'll see you next time on the Creation Podcast. We want to say a huge thank you to our members and patrons. If you'd like to see your name here and unlock perks like early access to our podcasts, members-only polls and live streams, behind-the-scenes footage, or exclusive video content, links are in the description below.